This is Daniel Coosberry, and in this lecture we're going to be talking about exponents and scientific notation. So let's start by looking at some basic properties of exponents. They're written right here. The first is called the product rule, which says if you multiply two numbers with the same base, so we'll call this b the base of the exponent, that big number. The little number is the exponent. If you multiply two numbers with the same base, that is the same thing as taking that base and raising it to the sum of the exponent's power. So let me kind of give you an example. So let's just say we have 2 to the 4th power, in which case 2 would be considered our base, and 4 would be the exponent. And say we're multiplying it by 2 to the 5th power. And so here we have another number with the same base and then exponents. According to the product rule, then, this can be simplified as 2, the exact same base, to the 4 plus 5 power, which is actually just 2 to the 9th power. So in other words, if you're multiplying two numbers with the same base and some exponents, you can just add the exponents together and simplify it this way. Okay. That's a little distinct from the power rule here. So here we have a number, here's the base raised to an exponent, and that whole thing is raised to yet another exponent. So it's some exponent to a power, which is why it's called the power rule. So when you have something like that, let's just say, let's use these same numbers again. Let's say we have 2 to the 4th raised to the 5th power. When you have something like that, you end up multiplying the exponents rather than adding them like we did up here. So we can simplify this as 2 to the 4 times 5th, 4 times 5 power, which is 2 to the 20th. So in the first case, you're multiplying two numbers with the same base, you add the exponents. Here you're raising a number with an exponent to a power, and you multiply the exponent. So you got to kind of keep those straight. And then the quotient rule works a lot like the product rule. It's just kind of backwards. So if you have two numbers that you're dividing with the same base and some exponents, you end up subtracting the exponent. So in this case, if I have, let's just say I have 2 to the 5th over 2 to the 3rd, just changing the numbers a little bit, this would amount to subtracting the exponents, 2 to the 5 minus 3, which is really 2 to the 2nd power, which all these are actual real numbers. I can stick this in my calculator and see what these numbers are. But if you wanted to simplify the exponents, that's kind of how you would do it. Let's go ahead and maybe finish the job and see. If I pull out my calculator and see what's 2 to the 9th power, I end up with 512. If I put 2 to the 20th, hopefully that's going to work. I get a huge number. I get 1, oh my goodness, 1048,576. Huge number. And 2 to the 2nd power is 2 times 2, which is 4. So, and there shouldn't be any sort of dot there. Whoops. All right, just pretend that dot's not there. That's not a decimal. But that's how you use these rules. Now there's a few other exponent rules on these next slides. The next one is the zero exponent rule. It says that if you raise some number to the 0th power, then that ends up being 1. So any number to the 0th power is 1. So that means in these examples, 5 to the 0 is 1. Also, if you take -7 to the 0, you're taking this whole number, -7, raise it to the 0 power. That's also 1. C is a little distinct because you have a -8 to the 0, but notice how it looks different than B up here, is there's no parentheses around the -8. Because of that, we're going to think of this as, let's take 8 to the 0 power and then multiply it by a negative, or multiply it by a -1. So based on what we know already from our order of operations, please excuse my dear Aunt Sally, we want to do the exponent first before we do the multiplication. So in this case, we have an exponent, and then we multiply by -1. So we got to do the exponent first. So I'll kind of demonstrate what this means. So this is -8 to the 0, if you want to think of it that way, which is really -1, because that's what 8 to the 0 is. And so in this case, the answer is -1 rather than +1. Now here, we had -7 in parentheses, in which case we think, let's multiply that by -1 first, and then raise it to the 0, which is how we just end up with 1, like any other case. So these two are a little bit different, even though they look really similar. So you got to keep it straight. When you have the parentheses around the negative number, you raise it to the 0, that's 1. If you don't have parentheses, you got to raise it to the 0 power first, and then keep that negative sign, which ends up with -1. We also have the negative exponent rule, which says that if you have some number, a base to a negative exponent, that's the same thing as writing that number as 1 over the base to the positive exponent. So in this case, we have 10 to the negative 2. We can write that as 1 divided by 10 to the second power. So that's what the negative exponent means. It really means that this whole base is in the denominator of a fraction, and the exponent is positive in that denominator. We can simplify this even further by writing 10 squared as 100. So this is 1 over 100. And same thing here. 5 to the negative 1 power is really 1 over 5 to the first power. And that first power, you don't even have to write. 5 to the first power is just 5. Anything to the first power is just that number. So 5 to the negative 1 is 1 over 5. That should be it for the rules. Now let's talk about scientific notation. Now this is something you've probably seen at some point in your life in science class in particular. Scientific notation is a way of expressing really big numbers or really small numbers a little more simply. It really comes into play when we have numbers with a lot of zeros in it, like B here, or if we have decimals that are really, really small and there's a lot of zeros after the decimal. But in a nutshell, scientific notation is expressing a number as some number times 10 to a power, in which case that number is a number between 1 and 10. So whatever our a is, it needs to be some number that's bigger than or equal to 1, but not 10. So in this case, let's look at letter A here. We have a 32,000. We have 32 and then a bunch of zeros at the end. Now we're going to hold on to these zeros in a second, because that's going to be what makes up our 10 to a power thing. But the 32 is something we want to express as a, but we need to express the number 32 as a number between 1 and 10. So here's how we're going to do that. We're going to write it as 3.2. That's some number between 1 and 10. It's 3 and some change. And then we need to express the rest of these zeros, and also the fact that we just put a decimal before the 2 here. We need to tackle all that when we add in the 10 to a power part. So what we're going to do is we're going to think, well, if this is really the number 3.2, so here's kind of what I did is I've made this 3.2. How many zeros, or how big of a thing, so what power of 10 should I multiply by in order to get back my original number? Okay, so here's some powers of 10 up here. You know, if I multiply by 10, I move the decimal 1 place to the right. If I multiply by 100, I move it 2 places. I end up needing to move it 1, 2, 3, 4 places to the right to get back 32,000. So my exponent on the 10 is going to be 10 to the 4th. If you do 3.2 times 10 to the 4th in your calculator, you'll get 32,000. And also, this is scientific notation, because this part is between 1 and 10, and this part is 10 to a power. So that's kind of how we're going to go about doing these. So B, you have 22 or 220 million, and so we have the same kind of thing going. We have a bunch of zeros at the end, and we have a 22 part. So let's express that as a decimal. Let's put the decimal right here. So this would equal 2.2, which is some number between 1 and 10, times 10, and then how many zeros do I need to multiply by to get this number back? I got 1, 2, 3, 4, 5, 6, 7, 8. So if I do 2.2 times 10 to the 8th, I end up with 220 million. Now C looks like it could be in scientific notation already, because I see a number here, and I see it's 10 to a power. However, this number here is not between 1 and 10, which means I still need to change this a little bit. So let's express that 630 as 6.3. That's kind of how we started the other two. But then I've also got a 0 here at the end here that I need to take care of. So if I wrote this as 6.3, I need to multiply it by 100, 2 zeros, to get that 630 back. So maybe we can write it like this. I need to multiply it times 10 to the second to get that 630 back. But I'm also multiplying it times 10 to the 8th. Oops, because that's what it told me to do. So if I end up doing all those things, I can simplify that by the power rule. This is 6.3 times 10 squared times 10 to the 8th. Let me simplify that, add the exponents. This is 6.3 times 10 to the 10th. And that's how we would simplify that. Now we can also use scientific notation to tackle really small numbers, so numbers with decimals and like a bunch of zeros before the number. And we'll do it in a really similar way. So here I see a decimal and a 0 before the 14. I'm going to take this 14 and write it as some number between 1 and 10. Let's write it as 1.4. In other words, I'm just kind of sticking the decimal right here. And then I need to multiply it by 10 to a power so that if I do that, this decimal ends up moving 2 places to the left this time to get my original number back. So if I multiply it by 1, 2, that's going to be 10 to the negative second power will give me my original number back. So if you put this in your calculator, 1.4 times 10 to the negative 2, you end up with 0.014, which is what we started with. You can do the same thing here. You've got 3 digits here, and so we'll just use all 3 of them now. We'll write this as 6.47. Notice that there's only ever 1 digit before the decimal because the number's got to be between 1 and 10. So this is 6, between 1 and 10, and then some change. And so I'm putting the decimal here, and I want to multiply it times 10 to a power so that I get my original number back. So if I think how much do I need to move this decimal to the left to get my number back? So I go 1, 2, 3, 4, 5, 6, 7. If I multiply it by 10 to the negative 7, I should get my number back. C is a lot like C on the last slide. We have something that looks like it's in scientific notation already. However, this number is not between 1 and 10, so we need to tweak it. So let's take this and write that in scientific notation, and then remember we got to multiply by 10 to the negative 7. So this is like something on the last slide. We'll write it as 9.7 times 10 to the 4th. 9.7 times 10 to the 4th. So that's that part. And then we have a 10 to the negative 7 that we got to take care of too. Okay, so now we have a number, our first number is between 1 and 10, and we just got to do some stuff here now. So let's use the multiplication rule again. We're doing 10 to a power times 10 to a power. We can add those exponents together. 4 plus negative 7, that gives me 10 to the negative 3rd. And then I have 9.7 as my first number, something between 1 and 10. So that's how you would do that one. It's very similar to the one on the last slide. We can use scientific notation to multiply numbers in a more, I guess, a more easy to use fashion. So if we have really big numbers or really small numbers and we need to multiply them, we can exploit scientific notation because it kind of breaks the numbers up into 2 parts. It breaks us up to like the number part and then the 0 part, and we can do the multiplication just using these. So since we have 2 times 10 to the 3rd and 3 times 10 squared, we don't have any sort of distributive property here. We just need to multiply all the things. So let's multiply the 2 and the 3. That'll give us 6. Let's multiply that. We'll just kind of multiply one part with another part, and eventually we'll finish it up. So if we do 2 times 3, we get 6. And if we do 10 cubed times 10 squared, well, we just add the exponents. That is 10 to the 5th. So that's actually going to be our answer because we started in scientific notation, and our answer is still in scientific notation. This is between 1 and 10, and this is 10 to some power. So that's actually pretty straightforward. It's actually kind of nice because we don't see all these zeros. They're just kind of summarized in this 10 to the 5th. Okay, we can do something similar here. We can multiply the 1.2 times the 2, and the 10 cubed times the 10 to the negative 5th, and we'll end up with something similar. 1.2 times 2 is 2.4. And then 10 to the 3rd times 10 to the negative 5th, just add those exponents, you end up with 10 to the negative 2nd power. And that's what you would do there. So the multiplication works out. Now notice that what we're not doing is we're not doing any sort of distributive property. We're not foiling or anything like that because we don't have like addition and multiplication. This is just all multiplication. So we're just multiplying 4 things together. So here we multiply 2 of those things. Here we multiply the other 2 things, and then we're still multiplying here. That's what that is representing. So we are doing this well. Division works in a similar way. We can divide the number parts, and we can divide the 10 to the power parts. So let's do 12 divided by 4, and let's do 10 to the 6 divided by 10 squared. This gives us 3. 12 divided by 4 is 3. And then the division rule says if you divide two numbers with the same base and exponents, you just subtract the exponent. So this will be 10 to the 6 minus second power, or 10 to the fourth power. So you just do subtraction there. And that's in scientific notation. Similarly, with this next one, we will do 6.3 divided by 3, and then 10 to the 6 divided by 10 to the negative third. And if we do that, we get 6.3 divided by 3 is 2.1. And then we'll do negative 6 minus negative 3. And I might need to write that one out because I'm doing negative 6 minus negative 3, which is really negative 6 plus 3, which is really negative 3. So that exponent got a little bit bigger, a little less negative, if you will. But that's how we'll do that one. So this is also in scientific notation still, which is nice. So this is probably a more realistic example where you end up with you start with numbers that have a ton of zeros and they're really kind of a pain to look at. The idea here is we can use scientific notation to make our lives easier by first converting the numbers to scientific notation and then doing the multiplication. So let's do that. Let's convert that 82 million into 8.2 times 10 to the 7th power. And if we do this right, this will look just like the last example. And then we'll convert this 3 billion to 3 times 10 to the 9th. I see 9 zeros, so that should work. And if I did that right, then this ends up being like example 6. So now I'll do 8.2 times 3, which is 24.6. And then I'll do 10 to the 7th times 10 to the 9th. So I'll add those exponents together and get 16. And I want to do one more thing because now I have a number here that's not between 1 and 10. I want to think about moving that decimal over to the left to get 2.46. And then I'll need to add a 0 here because I moved that decimal over. This will be 10 to the 17th. So that'll give me something in scientific notation. So if you do this in your calculator, you should end up with 2.46 times 10 to the 17th if you converted your calculator answer to scientific notation. It might do that for you. We can do something similar here. Let's make this a division problem just like in example 6, where the numerator is going to be 8 times 10 to the, should count, let's see, if I put the decimal there, 1, 2, 3, 4, 5, to the negative 5th, because it's a decimal. And this will be 2 times 10 squared, or 2 times 100, give you 200. And then do the division. So divide 8 divided by 2 gives you 4. And then 10 to the negative 5th divided by 10 squared, that's negative 5 minus 2 will give me negative 7. And lastly, here's an example of when you're likely to use scientific notation for, again, it's something you use for really big things or really small things. Here's the mass of an oxygen molecule. It's really small. It doesn't weigh hardly anything. But you know, it's so small you want to use scientific notation to kind of summarize that number. And this says find the mass of 20,000 molecules of oxygen. Okay, so if one of them weighs this much, then 20,000 of them will weigh 20,000 times that, the weight of any one of those. So this one's not even too bad to set up. We're just doing multiplication here. Now before I finish, let's convert this 20,000 into scientific notation, kind of like we just did. That's 2 times 10 to the 4th, and this is already in scientific notation. And now I can multiply these things together. 2 times 5.3 is 10.6. And then if I multiply here, I'm adding the exponents. So this is 4 plus negative 23, or 4 minus 23. This is 10 to the negative 19. And then I want to simplify this because, especially when you're dealing with molecules, things like chemistry, it is proper to have your answer in scientific notation. This is bigger than 10, so I need to move that decimal over. This will be 1.06. And then since I moved the decimal over, I'll need to increase this exponent by 1 to make all this the same thing. So increasing that negative 19 by 1 will actually make that negative 18. And that's going to be my answer. So we can say that 20,000 molecules of oxygen weigh 1.6 times 10 to the negative 18 power. And that should work out. Again, if you did this multiplication in the calculator, you should end up with a really small decimal that is just that. So that's a good example of like when you're actually going to use scientific notation and why these exponent rules and scientific notation are going to help you do these problems probably more quickly and efficiently.